Hello dear students, this is Jayant Mane from Lect Academy Ratnagiri. Welcome to the fifth lecture of drives and control. Today we are going to see the fundamental torque equation of electrical drive or motor load system. So you can see the picture in which a motor load system is shown. This is the simplest possible system wherein a motor having inertia J is directly coupled to a load and they are rotating in this direction with speed omega m radians per second. So in electric drives we generally represent speed in radians per second. In machines you are having habit of denoting the speed with n and its unit is revolutions per minute rpm, but here it is radians per second. So it is very convenient to express the speed in radians per second here in drives because we have to deal with some electromechanical systems. Load is mechanical one and electric is the motor is electrical. There is interaction between electrical and mechanical, so it is very advantageous in representing the system, the speed in radians per second. So here for this system J is the moment of inertia of motor load shaft. So it is the inertia at the motor shaft, we can say, and when load is also coupled on the same shaft, it is the total inertia, motor inertia as well as inertia of loads which are directly coupled to the motor. So when we calculate that inertia at motor shaft, that is what the J is. It is moment of inertia of motor load shaft. Its unit is kg meter square. Then omega m. So omega m is the speed, instantaneous angular velocity of motor shaft, and it is in radians per second. Capital T is instantaneous value of motor torque given in Newton meters. Similarly, TL is instantaneous value of load torque in Newton meters. So kg meter square is J, radians per second is omega n, and Newton meter the torques. Now from the laws of motion, from the fundamental equations or basic equations motion or Newton's laws, whatever is the difference between the motor torque and load torque, that can be given as this quantity. This is also torque, isn't it? Torque, one torque minus another torque, obviously it should be some torque. So this quantity is derivative of J into omega m with respect to time. So this is also a torque which is called as dynamic torque. Now see, when there is difference between motor and load torque, that means there is some net torque and it is a transient operation. And if both torques are equal, in that case it is T minus TL equals 0. When both torques are equal, it is called as steady state operation. So that means whatever is the load torque requirement, that is met by the motor torque, and therefore there is no resultant torque and there cannot be any acceleration or deceleration, and the motor load system runs with a constant speed, and due to that this term d omega m by dt, this term goes to 0. So that is called as steady state. So the motor load torque equation at steady state is T minus TL equals 0, and during transient operations it could be a positive or negative T j omega m by dt. So what is the meaning of this? Suppose T minus TL is a negative quantity, means load torque is greater than motor torque. So what physically should happen? Load torque is generally opposition to the motor torque, and if load torque is greater than motor torque, then there has to be deceleration, means reduction in the speed. So this quantity, this whole quantity is negative, so speed is reducing, or d omega m by dt, this term is going to be 0, like that, deceleration. And if motor torque is greater than load torque, in that case this dynamic torque quantity is positive and there is acceleration. So obviously there are only two possibilities, acceleration or deceleration, because load torque could be greater or smaller than the motor torque. So this quantity, means right hand side quantity, is present only during variable speeds or during transient operations of the drive. At steady state this quantity is 0. So this quantity is called as dynamic torque. So if we simplify this term, it's actually, this is a derivative of a product u into v rule. If we apply u into v rule, and if we assume that it is a constant inertia system, means load in the system, or you can say weight of the system is not changing. In that case it is a constant inertia system. In that case the dj by dt term is 0. So actually there is one more term here. So one term is j d omega m by dt, and another term is omega m into dj by dt. So this is dj by dt, means change in the inertia with respect to time. But if it is a constant j system, in that case this goes to 0, and therefore we can write only these terms. So this is for constant inertia drives. Generally the inertia of the drive is constant. So this is the dynamic torque. Which could be positive, which could be negative, and its sign decides whether it is acceleration or deceleration. It is also written here. The term j d omega m by dt is called as dynamic torque, which exists only during transient operations. So this is very important equation, which is called as fundamental equation of motor load system. Now this is the simplest equation, isn't it? And any complex load can be represented using this system, and then we can evaluate the performance of the drive. This equation is always used to evaluate performance of the drive. Performance is obviously steady state performance and the transient operation performance or dynamic performance. For example, in what time the drive could be reversed? Okay, because there is kinetic energy stored into the inertia j, and to slow down the drive or to stop the drive, to reverse the drive, we have to remove this kinetic energy from the drive. So obviously we cannot destroy the energy, so we have to convert it into some another form that requires some changes in the system, that also requires some time, isn't it? So deceleration means taking out some kinetic energy, braking or speed reversal, stopping within some time. It is, we have to remove the kinetic energy from the system. And to accelerate, and for increasing the speed, we have to increase the kinetic energy in the system. So J plays very important role in time of operation, transient time of the system. Then direction of rotation is also important, and all that. So all those performances, heat produced in the machine, all those performances can be easily evaluated using this equation. So we are going to use this equation in so many numericals, or while even deriving some equations. So this is the simplest equation, this is the simplest representation of motor and load system. So there could be multiple loads connected, okay, through some, suppose gear, this is a gear, this is one shaft, this is another shaft, and there is another load. So if this gear is running in this direction, then another gear rotates in opposite direction with some another speed, omega m2. This is having some different load torque and also having some different inertia. So such things could be there. There could be multiple loads connected to this load. So even in that case, we have to transform all these loads. So we have to transform this inertia to the motor shaft, this speed to the motor shaft speed, and this torque into the load torque. So how that can be done? So this gear system or pulley system which is there, okay, so if we connect some gear or pulley to this thing, so all those are just like transformer, electrical transformer. So this is having number of teeths on one side, number of teeths on another side. It is just like turns ratio of transformer. Then depending upon turns ratio, there is speed. So this shaft could be running with some one speed, and another shaft could be running with some another speed. So due to that, the speeds are different, but there is a ratio, constant ratio of the teeths. So we can easily transform the quantities to the motor shaft. So that is done. So that derivation we'll see afterwards. And there could be loads with rotational motions. There could be loads with translational motion. It's only up down. Suppose there is elevator, lift, it moves only up and down. So this is translational type of load. Or any compressor is having piston to pump air into the tank, and that piston moves only to and fro, like it is having linear motion. So some loads having linear motion, some loads, and many loads actually are having rotational motion. So any type of motion loads have to be transformed at the motor shaft. Their equivalent torque, their equivalent inertia and speed has to be calculated. Obviously one should consider the efficiency also, efficiency of the transmission. So if there is some gears, they are not obviously you can say transforming energy 100%. So there is some friction always between the gear tips, and some loss is there. It is just similar to the copper loss, core loss of the transformer. So the analogies of these mechanical systems are similar to electrical systems, so that those can be easily understood. So I have explained many things, I will just go through the points so that nothing can be missed out. Okay, so when motor accelerates, motor should not only supply the load torque but also an additional torque component, which is J d omega by dt, in order to overcome the drive inertia. So to acceleration, as for acceleration, motor torque should be greater than load torque, in short. During deceleration, just opposite, dynamic torque has a negative sign, therefore the load torque is greater than motor torque. So the dynamic torque assists the motor develop torque and maintains drive motion, its kinetic energy. Okay, so this is what the fundamental torque equation is, very important equation, and this equation we are going to use while solving so many numericals and for very many derivations. Okay, so any form of this equation is fine. Means T minus TL equal to J d omega m by dt, that is one form, or this form T equals TL plus J omega m by dt. Actually it could be plus and minus. The sign of this dynamic torque depends on the magnitudes of motor and load torques. So this is about fundamental torque equation of motor load system or a drive.